Okay, so the semester is almost over. We have one more lecture left after today. Unfortunately, on Tuesday, we will not be having a lecture. So today, I will rather start discussing the Maxwell's equation rather than continue with the circuits. Now, do you have any questions before we start? Today I will start the Maxwell's equation. Depending on how much we can proceed, on Thursday, we will go back and review the circuits also next week. Now, before we continue, do you have any questions? Now, up to now we have studied various equations that allowed us to determine the electric and magnetic fields everywhere. Now, what are they? Do you remember the equations we had? We have the Gauss law, which is E dot ds is equal to Q enclosed divided by epsilon 0. Now, this is one property that the electric field should satisfy. Any other property of the electromagnetic fields that you remember? Somebody else? What else do we have? Some other person rather than some other voice. Okay, any one of the laws that you remember? Okay, E dot dl, this was equal to minus d phi b by dt, which was minus over the area b dot dA. Okay, this is another law we know. We also know for the magnetic field, we know b dot ds is equal to 0. This is basically the statement that the magnetic fields do not start, field lines cannot start at a point and they do not terminate at any point. This equation tells me that electric field lines can start from charges or end at charges. This equation tells me that there is no charge for the magnetic field lines to end or to start. Or said in another way, this equation tells us that the magnetic monopoles do not exist. Now, what does this name mean, monopole? Well, we had already studied dipoles. If you remember what the dipole was, we have the minus charge, minus point charge, plus charges. They are slightly displaced. That is what we call the dipole. It has 2 points. A monopole is just a single point with a single charge. That's what we call a monopole. A point electron, for example, is an electric monopole. We have electric monopoles because of this law, but as far as we know, until now, we fail to observe any magnetic monopoles. And finally, no, this is not. And then we have B dot dl is equal to mu 0 I. Now, these 4 laws summarize the properties of the electric field. You can just think of these 4 laws as the F is Newton's third law, the 3 laws of Newton for mechanics. The 3 laws of Newton for mechanics describes all the mechanical phenomena, and these 4 laws almost describe all the electromagnetic phenomena. Everything that you can think of should be described by these equations, almost. There is just one inconsistency in these equations, one problem. Now, if you remember, we obtained this law. We said that there was an inconsistency in our equation and that we had to have this term by just looking at the properties of the charges in a magnetic field from different reference frames. We said that, okay, let me just add one more equation here. Now, with this law, these equations plus Newton's 3 laws describe all the phenomena almost all the phenomena that you see around you. It's enough. These laws plus the Newton's laws are enough. There is one inconsistency left. Now, to solve one of the inconsistencies, that is the independence of acceleration from reference frame to reference frame, we had to add this term. We had to say that if we have a changing magnetic field, or if the magnetic field lines are moving, in that case, they should be generating some electric field. Otherwise, the acceleration of a point charge moving in a uniform magnetic field depended on which reference frame you were in. Now, this changing magnetic field, the magnetic force changes as you go from one reference frame to the other reference frame, but so does the electric field change. So these two changes, because in a different reference frame, the magnetic field will be moving, changing, and it will create an additional electric field, and hence the acceleration would be independent of reference frame, thanks to this additional term over there. Now we will still have one more inconsistency. Now let's look at this equation over here. This one. Now let me also write the Gauss law in a different form. Now this is, the total charge is nothing but the integral of the charge density over the volume inside our surface over here. Now let's go back to this one. And we had already studied this law. We said that, okay, if we have an infinitely long or almost infinitely long wire, if it carries a constant current, we said that because of this law, we will have a magnetic field lines that is going around this wire. These are the magnetic field lines. It will be just circles around the wire. And furthermore, we also know that the magnitude of this magnetic field lines is mu0 I over 2 pi r. Okay, this equation should be valid if the wire is infinitely long and straight, and or if we are very close to the wire, it will. I mean, the issue is what infinity doesn't have any meaning. Infinite doesn't have any meaning, so we can only say a very long wire. But a long wire. So what is long? How do you define the long? You have to compare it with something else. So here you have two lengths, the length of this wire and your distance from the wire. If the length of the wire is much larger than your distance from the wire, you should have this magnetic field. Okay, so how do you determine the current? Okay, you connect an ammeter to a wire, then you measure it, but what's the underlying principle? How do you determine an arbitrary current? What was the definition of our current? Okay, the current, we defined it as dq by dt. What is dq? Which charge? Moving through what? Moving through the cross section. So basically what you assume is you just take some area. This is your area. Some charges will be moving through it. Then you count how many charges move through this area. That is our dq. And then divide it by dt. The time it takes for the charges to cross that area in the perpendicular direction. That is how we define the current. So we first assume an area. We count the charges that goes through the area, and in a given time, we measure the time, we count the charges. So the dq by dt, the charges divided by the time, just gives us the total current. Now so which area are we considering here? We have this closed loop, we have this area. Which area are we talking about here? Well, it is basically an area that remains inside this loop, right? So you assume you can take this area. That is your area. That's your surface. You just count the charges that pass through that surface in a given amount of time. You just take the ratio that gives you the total current enclosed by this loop. This is enclosed. But this is just one possible surface. We have many surfaces that is bounded by this closed loop. I can imagine such a surface. This is also a valid surface. And whatever charge passes through this surface also passes through the other surface. So whether I take this surface or this surface doesn't have any effect. The I would still be the same. The magnetic field on this loop doesn't change, so I enclosed should be constant, should be the same whichever surface I consider. Well, if there is no accumulation of charge at any point inside, in this case we had assumed that there is no accumulation of charge anywhere. So whatever charge enters into this volume should also leave that volume. So the current passing through this area is the same as the current passing through this area, this surface. Clear or no? It's independent of the shape of this closed surface. You see, the loop that we consider over here, this closed loop, I mean, almost all the time we imagine it to be a flat loop. Thus it lies in a plane, but even this can have an arbitrary shape. It doesn't have to be flat. These laws will still be valid for this closed loop, for that arbitrarily shaped closed loop. And to define this current, we can just take into account any surface whose edge is this closed loop. Now, up to here, there's no problem. This equation holds whether we assume the current passing through this area or the current passing through this surface. This law still holds. There's no inconsistency. But now let's imagine that at a very far away from this wire, we have a capacitor. So there we put a capacitor. Now, we already said that as long as we are very close to the wire itself, this should be our magnetic field. Whether there is a capacitor at very far away distance or not, doesn't change the magnetic field, as long as we somehow manage to keep the current constant. So we just increase the potential that we apply, because as the capacitor becomes charged, we have to increase the potential that we apply of the power source to keep this current constant. But we keep it constant. And as long as we keep it constant, the magnetic field will not be affected by this capacitor over there. Now let me imagine another surface. Now we already said that to define the current, we can choose an arbitrary surface. It's just a mathematical surface that we are imagining it. This surface can go to infinity or almost close to infinity and come back. There's nothing that prevents us. But now we see you should be seeing the inconsistency. B doesn't change. B is the same whether I imagine this surface or the other surface. So B dot dl is always mu0 times I. But there is no current passing through this big surface. There is no current passing through it. So if we define this I enclosed, now what we are actually doing is I enclosed, we said that it is the current density integrated over the surface that we are considering. Now if I take this huge surface, there is no current passing through it. So for such a surface, this law doesn't hold anymore. Because on the left-hand side, or let me write it this way, B dot dl, the integral of B dot dl around the closed loop is equal to mu0 J dot ds. Well, this law doesn't hold anymore for this surface. Now, it should hold. I mean, if you want to write a law that depends on some arbitrarily defined quantities, like the closed loop over here and the surface that you choose to calculate the current, your law should be independent of which surface or the closed loop you choose. It should be valid for everything. But apparently, this law is no longer valid. This doesn't hold if we imagine such an arbitrary surface. So we should add something that will fix this law, that will fix the problem with this law. Now, we had already seen that a changing magnet, I mean, if you look back at these equations, they look quite symmetrical. I mean, this law just looks like this one. The only difference being is here we have electric monopoles. We don't have magnetic monopoles, but they look almost identical. Well, this law and this law, they also look identical, almost. But here we see that the magnetic field changes and it creates an electric field. We don't have the other case around. The electric change in the electric field doesn't create any magnetic field if these laws are correct. So maybe one thing we can modify here, if you just like the symmetry in these equations, one thing that you should modify is that if a changing magnetic field creates an electric field, a changing electric field, it would be nice if it creates a magnetic field. Now, will that solve this problem? Is there a changing electric field here? On this surface, there's a changing electric field here. Now, what is the charge in the capacitor? Or let's say dq by dt. Okay, oops. Okay, it didn't like it. Okay, your last chance to hand in your homework. Okay, so these were our laws. We have E dot ds is equal to Q enclosed. And E dot dl integrated around the closed loop, this was minus B dot ds. B dot ds integrated over a closed surface, this was 0. And B dot dl, this was equal to mu 0 I, or mu 0 J dot ds. So these are our equations. And then we said that, okay, let's imagine this infinite, very long wire. We have this very long wire. There is a capacitor at some point. Now, at a point very far away from that capacitor, we take this closed loop. We consider the integral of B dot dl. And we consider it for this surface or for such a surface. And then we said that now for the first surface, B dot dl is nothing but J dot ds times mu 0. But then we had this problem for this huge surface. On this surface, there is no current density because the wire doesn't pass through my surface. But what happens is I have an changing electric field inside the capacitor. Now let's look at do you remember what is the electric field inside the capacitor, the magnitude of the electric field? Now we have a parallel plate capacitor. Let's say it has a charge Q, area A. Then the electric field is just Q over A, 1 over epsilon 0. It's the charge density divided by epsilon 0. This is the magnitude of the electric field. So what is Q? You can just solve Q from here. Q is nothing but epsilon 0 E times A. Okay, what is E times A? What is E times A? It's the electric flux. The electric field is uniform over the area A. So the electric flux is nothing but the E electric field magnitude times the area. So we can just say that, okay, Q is equal to EA times epsilon 0. But we know what the current is. Current is dQ by dt. But this is epsilon 0 d phi E by dt. So although there is no current passing through this huge surface, okay, there is no current passing through this huge surface, there is a changing electric flux on this huge surface. And the current in the wire is equal to epsilon 0 times the rate of change of this flux. So I can correct this equation. I can just say, let me copy this. I can just add this term, epsilon 0 times E dot ds. Or let me rewrite it, B dot dl is equal to mu0 J dot ds plus epsilon 0 E dot ds. Now if I write it this way, now let's look at this term over here. So what do we know? If we take this small surface, J dot ds is equal to the current running through my wire. Because there is some current density passing through this surface, and the integral of that current density over this surface is nothing but this I, the current running through my wire. And there's no electric field that is passing through my wire, through this surface. So this term is 0. I have this term. If I take this small loop. On this surface, remember, I am very far away from this wire. I'm looking at here. So E dot ds over this surface will be 0. I'm very far away. Now, we will consider the case when this surface is not that far away. Well, you see, okay, there is an electric, okay, one thing, if you assume that the wire doesn't have any resistance, there's no potential difference across the wire. So there's no electric field, or negligible electric field. Even if there is an electric field, you can assume that the cross-section is negligible. So then there won't be any contribution. Okay, if you assume this larger surface, Okay, there is no current density passing through it. There is an electric field, and the electric field is non-zero only in between the plates. And we have just shown that, now here we have the rate derivative. We had just shown in the previous slide that the derivative of this electric flux is nothing but equal to the current, which is this term. So for the small surface, we have this term that is equal to I. For the big surface, we only have this term which is equal to I. For both surfaces, this sum is equal to I. So this law is valid whether I consider this surface or this larger surface for the integrals over here. So this is our new correction to our Maxwell's equations. Now let us also discuss one more case. Now I have this wire. I imagine this loop over here. This is my capacitor. And I imagine such a surface. I can imagine this surface or this larger surface. And remember, B dot dl is equal to mu 0 J dot ds plus epsilon 0 d by dt E dot ds. Now how does it work? Okay, for the small surface, for this surface, it's kind of clear. There's no electric field in this region or negligible electric field in the region. We are assuming that all the electric field is only inside this parallel plate capacitor. We can imagine these parallel plate capacitor to be very thin and very long, so there won't be any fringing fields. So this J dot ds for this small surface is nothing but the current running through my circuit. Now for the larger surface, now the flux that is passing through this larger surface is not the full flux. The flux will be smaller because this larger surface doesn't cover the electric field or the electric flux in this portion of the capacitor. So this term will be smaller than the total current. So this term will be smaller. So how can we still say that this whole thing will be still mu 0 I? We know that if this surface covered all of this capacitor, then this term only would have been I, the current. But it's not doesn't cover the whole capacitor, it just covers a portion. So this term by itself is smaller than I. So where is the rest of I? No, we are not. No, I mean, we are neglecting the electric field. There is no mistake over there. The current is more obvious, let's say. Where is the additional current? Now, this term is still there, but it is smaller. This term has to be there. Do you know where the current passes through my surface? There's a current over here. You see the charges, as the current is running, the charges will arrive at this capacitor at this point. And then they will be distributed over the plates, over the conductor. But if as they are being distributed over the conductor, they will also pass through my surface. So I have a contribution from this term also. Now for this surface, both of these terms contribute, not just this one. And this term contributes because of this part over here, where as the charges are distributed over my plates, they have to cross my surface. So I get some actual current created by the charges passing through my surface. And the sum will still be mu 0 I. And these are our 4 Maxwell's equations. Yes? Yes? Now the potential difference between 2 points we had defined as the integral of E dot dl, L, over a line, not over a surface. Of course, if there is no changing magnetic field. Now we have, this completes the 4 Maxwell's equations. E dot ds is equal to Q enclosed over epsilon 0. E dot dl. Well, this would have been the potential difference if there is no magnetic change in the magnetic field. Is equal to 0, and B dot dl is equal to mu 0 I enclosed plus ID. This ID we define as 1 over epsilon 0 d by dt phi e, the electric flux. This is called the displacement current. It's just a historical name. There's no current there. The charges are not moving there. We might have some charges, but not much. What it means is that along this wire there is a current. Charges are moving. But when they reach such a capacitor or a similar place, region, there will be this changing electric field built inside this region, and that changing electric field somehow displaces the current. It takes the place of the current. So that's why we call this displacement current. There's no charge motion over there. And these 4 equations are enough to describe every electromagnetic phenomena. Yes. Whatever electromagnetic phenomena you can think of can be described by these 4 equations. If you add the Lorentz force, then all the mechanical and electromagnetic phenomena you can describe. Almost everything that you can see around you can be described by these laws, plus Lorentz force and the Newton's laws. That's enough for everything that you see around you. Now, any questions up to this point? These are called the Maxwell's equations. Now, these are their integral forms. You can also write these as differential equations, but at this year, you will only see them as integral equations. You see, for example, Newton's law is a differential equation. It relates the second derivative to some other functions that we call the force. These are integral equations in the sense that they relate the integrals of the electric and magnetic field to the charges and the electric and magnetic fields themselves. And of course, they're time derivatives. Now let's do an example and let's see an application of this one. Do we have any electric field? How can we calculate this electric field? No, this magnetic field created by this changing electric field. Now let's just imagine we have a capacitor which is large enough, thin enough, and so we have at a given instant there will be some charge on it. Let's say the area is A, the distance is D. Now what is the electric field in it? In between these parallel plates. Electric field, the magnitude was Q over A times 1 over epsilon 0. And it is pointing, let's say this is the positive plate, this is the negative plate. It will be pointing from the positive plate to the negative plate. Okay, first of all, we will just see in a moment that if Q is time dependent, this will not hold. But as a first approximation, we can say that, okay, this is the electric field between the plates. Now, rather than looking at the plates like this, let us just look at it from the top. So what we will see is, let's just for simplicity, let's assume the plates are spherical. So this is our plate. And we have a uniform electric field that is pointing into the screen. Okay, these are uniform. And, well, in this region, in between the plates, there are no charges, hence there are no currents. So if there will be a magnetic field, it will be due to this term. So what will be the shape of these magnetic field lines? First question. Now, in order to use this law, we first have to be able to express well, we can calculate this one, there's no problem with that. But we know the electric field, so for any surface in principle, we can calculate this flux, but we cannot calculate this one without knowing the magnetic field. And it's the magnetic field that we would like to know. So we have to first express the magnetic field in terms of some unknown functions, such that we should also choose this closed loop such that we can evaluate this integral, although we don't know the magnetic field. And in order to do that, we would first have to determine some properties of the magnetic field. Now, what can you say about the magnetic field generated when the current is changed, the electric field is changing? Okay, it will be perpendicular to the electric field, fine. What else can you say about the direction of the electric field? For example, they can be radial or of the magnetic field. They will form closed loops, and they cannot be radial because we already know that since B dot ds is equal to 0, you see, this holds all the time. And since B dot ds is equal to 0, the magnetic field lines, they cannot start or they cannot end at any point. So they cannot start from a point. They have to form closed loops. Now, what will these loops look like? That is the crucial thing. Well, the capacitor plates are symmetrical. They are that's why we have chosen them to be circular. Since they are circular, if we rotate these plates around their axis, central axis, nothing changes. So the electric field and nothing changes. It should be also true for the generated magnetic field. If we rotate this system around the central axis, nothing should change. But that already tells me that these closed loops of magnetic field lines, they should just be circles around the center of this. So this is a magnetic field line. Let's say this different distance is, let's call it rho. Now, it tells me that this magnetic field is some function of rho only. It cannot depend on anything else because of this rotation thing. And let's say let's call this direction to be the theta hat. Now, so the magnetic field is in that direction. And dl. Let us also choose the direction of our loop. To be in the same in this direction. So dl is dl in the theta hat direction. So here we need to evaluate this b dot dl, and I have chosen this circle to evaluate b dot dl because on this circle, this unknown function is just a constant, and the constant I can just take out of the integral. That's why I chose this circle. So b dot dl is equal to, well, This is how I define the B. I know that B has to have this form. I don't know what this B rho is, whether it's positive or negative, I also don't know. And I can choose the L in this form. Now their scalar product is nothing but B rho times dl, again around this closed loop. And since B rho is now constant around this loop, I can just take this out. What remains is the circumference of the loop. So this is equal to 2 pi rho times B of rho. Okay, this is one thing I have. So I already evaluated the left-hand side. Now, what is the flux that is passing through this area? We have already said that the electric field is Q over A times 1 over epsilon 0. Now remember, A is the area of this plate. Should I calculate the flux that goes through this plate or through this area? Now, in this law, now we choose this closed loop, and the flux is the flux that goes through the loop that we have chosen. So here we chose this loop, so the flux that goes through this loop will be just E, which is uniform, Q over A epsilon 0, times the area of this system, which is nothing but pi rho squared. Okay, this is so this is the flux. Of course, we have to multiply it by mu 0 epsilon 0 and take its derivative. Now, we will see. As a first approximation, let's just assume this one still, because that is what we know. I mean, we don't know that it is not valid anymore. There's mu 0 over here, epsilon 0 is over here, this is epsilon 0. So this is the equation we now have. Is it plus or minus flux? Minus or flux? Minus or plus? How do you determine whether it is minus or plus? Right-hand rule, curl your fingers around your loop. This is the positive direction of your flux. But our flux is moving in the opposite direction. So we have a minus over here. The flux is minus this term. So let me make some simplifications and rewrite everything. This epsilon 0 will cancel this one. So B rho is just mu 0 over 2 pi minus Q as a function d by dt of Q times rho. By the way, this can also depend on time t. There is nothing that would prevent the magnetic field to be time dependent. So we have a time dependent magnetic field which is given by this expression. This is the B rho of t. There's a minus sign. So the magnetic, if the charge is increasing, if the electric field is increasing, then the magnetic field lines are not going in the counterclockwise sense, but they are in the clockwise sense. Now, why did I say that this is not exactly true anymore? Now, what we have here, we have these two parallel plates, okay? At a given instant, there's a charge on these plates which will be changing in time, this Q. So we said that, okay, if the electric field is given by this expression, in that case we have a changing electric field. This changing electric field creates a magnetic field. This one. Now, it is possible that dq by dt is just a constant. Well, if you just send a constant current in your system, then the charge dq by dt is nothing but equal to the current that runs to your capacitor. If that current is constant, then dq by dt will be a constant. The magnetic field is independent of the charge. The magnetic field is independent of time. You have a constant magnetic field. But if the current itself is time dependent, for example, we already know that if you take a capacitor, connect it to a power source, power supply, whether a DC source or an alternating current, well, then the charge in the capacitor will be time dependent. Furthermore, the current will be time dependent. If the current is time dependent, you have a changing magnetic field. Now, we started from a changing electric field, which created a changing magnetic field, but we already know that changing magnetic field creates a changing electric field. So we have to correct this expression by calculating the electric field created by this changing magnetic field. Yes. Furthermore, you have to add, okay, you have this changing magnetic field will create a changing electric field, which will be a correction to this one. But if you have a second term over here, that second term, that additional changing electric field will itself create a changing magnetic field. And so you have an infinite expansion, just like the Taylor expansion. In this case, it won't be a Taylor expansion, but nevertheless, you have some expansion of many terms. It will depend on whether dq by dt is changing in time or not. And you see the first term, the magnetic field, the electric field created by this changing magnetic field will be equal to the second derivative of the charge. And then the magnetic field that changing electric field creates will be the third derivative of the charge, etc. So you will all get higher derivatives of the charge. Well, if the derivative is 0 at some point, then that's fine. You have a finite number of terms. Otherwise, you have infinitely many terms. Now, any questions on this one? That's not charge density, that's the distance. You see, this distance is rho. Rho is not charge density here. Let's have a quiz. You have 5 minutes for the quiz until 1:40, and then you have 10 minutes for the break. I have a region where I have a uniform magnetic field. Let's say the magnetic field is in this direction. I put a surface inclined like this on this magnetic field. The surface has a total area A. You can just assume it is a circle. And so the angle that this vertical the normal direction makes with the magnetic field is called theta. What is the magnetic flux?